Bismillahirrahmanirrahim. So we are going to start our third lecture, and we have already learned about the presentation of a analog signal as well as the presentation of a discrete signal in detail in the last few classes. So today we are trying to start the characteristics of the discrete signal. So we have learned about this analog signal, mostly the period, the frequency, the concept of the frequency. And similarly, we have talked about this discrete signal and try to understand deeply the representation of relative frequencies in different format, where small f is cycle per sample. That was very important to understand. Okay, so today we'll talk about the discrete time sinusoids are characterized by the following properties. What are the properties? So this is number one property. So first we'll talk about the first property, then the second and the third. So there are three properties it's listed in the textbook. So what is the first property? Okay, so the discrete time sinusoids is periodic only if its frequency f is a rational number. So the rational number means you have a ratio, let's say k and n, where both of them are integer number. So that is the definition of the rational number. So from this definition, so this is the statement. Now there is a proof. Okay, so I'd like to give the proof both mathematically, also by try to understand the fact with graphical representation. So what we are talking about? We are talking about the period of a discrete time signal. So that is our main concern. What is the period of discrete time signal? Let's say the period can be represented as by the capital N. So in case of analog signal, we know that how to represent the period. We have already represented that. If XAT is an analog signal, after XAT plus TP, we have the same signal. If that is so, then TP is the period of the analog signal. Now, what about the discrete signal? It represents like this. If Xn is your analog, your discrete signal, then if and only if after capital N samples, you have the same phase, you got the same phase, then the capital N is known as the period of the discrete signal. So it can be represented like that. After capital N samples, you have the same period. For example, we have drawn it in the last class as well. Let's say we have this kind of signal. Of course, you need to understand that you might have a periodic signal in the analog domain, not analog, the continuous time domain, but it might not have the period in the discrete domain that we are trying to represent today. Okay, so let's say this is the first sample, this is the second sample, third sample, fourth sample, and so on. So how do we find the period of the discrete signal? So you can count it like this is number 1, 2, 3. So these three sample, the number 4, this is 0, 1, 2, 3, 0, 1, 2, 3. So that means this is the number 1, number 2, number 3, and number 4. These 4 sample, after 4, this 5th sample belongs to the next cycle. So how many samples you need to represent this cycle? The full cycle is number 4. This 4 is the period of a discrete signal. Okay, it could looks like very simple, but what is the difference between the analog and the discrete signal now? So if I can consider the facts, okay, so you can follow those points. Okay, so we have those points now. We have sampled the analog signal. Where is the analog signal? This was your analog signal. We have sampled it with a specific time period, let's say T1. So where is T1? This is T1. So that means it represents a sampling frequency fs1. Now you can change your sampling frequency as fs2. Definitely, as an engineer, you can change the sampling frequency, and you have chosen the sampling frequency in such a way that now the points are like this. Now the points, let me choose another color. Okay, now the points are there. 1. So if this is an equal distance, it might be looks like this. It might be looks like that. I hope you can follow me. So this is the first and this is the second sample. In between, what is the time duration? The time duration is now T2. So where T2 is less than T1. Okay, it might be greater than. So here we have taken or chosen the T2 less than T1. So after the second sample, this is the third sample, this might be fourth sample. This is the approximate diagram. Okay, so from this diagram, can you tell me what is the value of capital N? Capital N means the period of the discrete signal.
5.
Sorry.
The value is 5.
Okay, so again, please raise your hand so that I can give you the floor. Yeah, you have mentioned that this is 5. No, the answer is not correct. Why? You need to search for the same period. For example, you have started with this. So you know about this the phase. Sorry, you need to search about the same phase. So this is, let's say this is a sample number 1. This is 2. This is new 3. This is 4. This is 5. At the location of 5, have you had the same phase as the sample of 1? No. The answer is no. Then what about the other sample, 6 sample, the 7 samples? Maybe you are proceeding more and more, but how many samples you might need? Okay, it might happen that after 104 samples, maybe this is a hypothetical example, after 104 samples you have the same phase as the sample number 1. It might happen. So what I have meant here, let's say you have a signal. So how many is, okay, so there is a number of cycles in the analog domain, and you have found it after a long period of time, you will get the same phase. Before and after that, you have the samples in equal distance, you have the samples, but still you are not finding the same phase. You are struggling to find the same phase. Okay, you are struggling, so you can't find the same phase. You are very close to that, and eventually in some point you are finding the same phase. Okay. On the contrary, it might happen that, okay, you have the red dots here. I'm putting the red dots, and red dots. If you follow the red dots, In that case, what is the value in case of red dots? What is the value of capital N? What is the value of capital N in case of red dots? If you have sample like that, yeah, 90. Yes, 90.
Yes, sir. The sample is 4.
The sample number is 4. That is the period. So we are talking about the period of the discrete signal. But what about the black dots? If you count the black dots, in that case, what is the period of that one? So in that case, of course, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21 belongs to the next cycle. So that means it is 20. So I believe you can understand that if you change what? If you change the sampling time, or you can say sampling frequency, that can change the period of a discrete signal. What about the analog? What is the period of the analog signal? Yes, it is always from let me choose another color. So it is always from this to this. So that was the period for the analog signal, TP. But the period of the discrete signal actually depends on what? Depends on the sampling frequency. So you are not sure about the period of the discrete signal always. It might changes. It might changes with the sampling frequency. And that's why the condition is that, so we'll prove that it might happen that you don't have the period. That means it might be that a analog periodic signal can be converted to a periodic signal of the discrete domain. It might happen. That means you never find this sample with the same phase. It might happen. If you are unfortunate, okay, don't think that the signal is infinitely long. If this is a finite, let's say your signal is up to this, in that case, we can say that, okay, the period for the black dots, you don't have any period for this discrete signal. It might happen. Okay. So what is the condition to get the period? So it's mentioned that the frequency, the discrete frequency should be a rational number. So the discrete frequency like f, discrete frequency means the relative frequency should be a rational number. A rational number means the representation of two ratio like k and n, where k and n are the ratio of two integers. Okay, so that is called a rational number. Okay, so let me represent those things by mathematical presentation. I believe that you understand the facts what I try to make you understand. Okay, the smallest value here, the smallest value of capital N for which the upper relation, this relation is true, is called the fundamental period. It's very simple. Like if N is equals to 4 samples, similarly the 8 samples, 12 samples are also the period, but the lowest possible value is called the fundamental period of a signal. Now this is the mathematical proof. Okay, so here let's start with this. As we have already know that the represent of a discrete signal can be like cos twice pi f0 n plus theta. Okay, so that is our xn. Now what we have done, we are proceeding more capital N samples. So here, how many samples you have? You have n samples, small n. Now you are adding more capital N samples. So then we can write it like this. cos twice pi f0 and now a small n plus capital N. So we are adding more n sample plus theta, and that we have already written here. Okay, so from doing the trigonometry, you know that, okay, we can write it like this, and this part could be is equals to this one if and only if this portion, that means twice pi f0 capital N, where what is the value of f0, what should be the value of capital N. So that portion, that means this portion, that means twice pi f0 capital N should be like twice pi k, where k is an integer. So you can say k is like 1, 2, 3, 4, even it can be start with 0. That means in a cos, if you have twice pi, every after twice pi you have the same value. Every after twice pi you have the same value. So you don't have any impact to the output or output signal. So that's why after twice pi you have the same value. So what does it mean? If and only if this part is equals to twice pi k, where k must be an integer. In that case, of course, we can say that this equation is equals to this, because in that case there is no impact of twice pi f0 n. Okay, so you don't have any impact to the signal. So that means you have started with this and you come with that one. So then what you can write that, okay, if x n plus capital N, you start with this, is equals to xn. What is the condition? The condition is twice pi f0 n should be is equals to twice pi a integer number. That is the condition. If this condition is there, then you can write like this. In this way, what we can make the relation between f0 and k. What is the value of f0? The f0 is nothing but k by capital N. We have already declared that capital N is an integer number because that is a period, and k is also declared as an integer number. Otherwise, it will not be possible with this equation. That equation means twice pi f0 capital N is equals to twice pi k. In that way, we can prove that only then we have f0 is equals to k by n is a condition for making the capital N is a period of the discrete time signal. So in that way, we can prove that the f0, that means our frequency should be equals to k by n, which is a rational number, and we have proven that. Okay, so I have written something more, so you can go through this and you will find it probably more convenient to understand the fact. So a discrete time sinusoid is periodic only if its frequency f0 can expressed as the ratio of two integers. We have already proven that. To determine the fundamental period of capital N of a periodic sinusoid, we express its frequency f0 as in equation 1. So what was the equation 1? This is k over n, and cancel the common factor so that k and n are relatively a prime number. So what does it mean? If we have f0 is equals to, let's say, 20 divided by 60, then we can move it to like 1 divided by 3. So then what is the value of capital N? The capital N is equals to 3. At the very beginning, the capital N looks like 60. Okay, fine. 60 is also a period. However, the lowest number of capital N is the fundamental period. So the fundamental period is 3 here for that example. this is a very important statement, and try to understand this. Observe that a small change in frequency, which frequency? The analog frequency. We're talking about the analog frequency, can result, sorry, we are talking about the discrete frequency, can result in a large change in the period. Again, I will repeat the things. Observe that a small change in frequency, which frequency? It can be discrete frequency or it can be analog frequency. Okay, because as we already proven that if the analog frequency changes, that means it is decreasing, of course the discrete frequency also decreases. Okay, in future we can show that the small f is equals to f over fs. We'll show that today, inshallah. However, graphically we have already shown that if capital F increases, the small f is also increases. Capital F decreases, small f will decreases. So a small change in frequency can result in a large change in the period of a discrete signal. Period of a discrete signal. For example, the example is given here. If f1 is equals to 31 over 60, implies that what is the period? Of course, this is 60. What kind of period is that one? This is, of course, the discrete period, discrete time signal period. However, if we change this number like this, 30 divided by 60 implies that the period is this one. Okay, let me ask you one question. What does it mean by this? F1 is equals to 31 by 60. Because in the previous day, in the second lecture, we have understand the definition of F. So from the definition, how you can mention the value of F1, how you can define the F1. Physically, can you draw this 31 by 60? What does it mean by F1? If I can give you some hints, what is F is equals to 1 by 4? What does that mean? F is equals to 1 by 4.
It means that the period is 4.
From the previous class, not from this class. Whenever I have defined the value F first, what is the definition of F? You need to raise the hand before giving the answer. What is the definition of small f? Yeah, 132.
Sir, sampling frequency?
No, that is not a sampling frequency. Yeah, 58.
Sir, it needs 4 samples to complete 1 cycle.
Exactly. That is the definition. So by the definition, that is a cycles per samples. Forget about that. Cycles per sample. That is the definition. But you need to understand it by the graphically. So it means that you have a full cycle. For full cycle, I have already mentioned it for several times. So how many samples you need? In 1, 2, 3, and 4. The 5th cycle belongs to the next cycle. So you need 4 samples to represent 1 cycle. 1 samples need 1 by 4 cycles. So that is the definition of small f. What is small f? That is the relative frequency. Okay, these are the very simple definition, but you need to understand it graphically. Okay, now can you tell me what does it mean by this? F1 is equals to 31 by 60. What does it mean? Can you draw that? Yes, 58.
Sir, is it it needs 60 samples for completing 31 cycles?
Exactly. And after that, you are getting the same phase. And that is why this is the period. So you can think of So how do you represent this graphically? That is most important thing. If you have this, okay, let me draw it like this. So these symbols mix, this is a break. Okay, this is a break. So you have one cycle, two cycle, and continued, and then let's say this cycle is the 31st cycle. This is the first cycle, this is second cycle, and that will continue up to, and this is, let's say, this is 30th cycle, and then this is 31st cycle. And where are the samples? I have already mentioned that. Okay, let's say it starts with this phase, so you are searching for that phase, and after 31 sample you got this, and before that you have the samples like this. Okay, so arbitrarily I'm just putting this, just not any scale, so I'm putting like that. Okay, so how many points? This is 1 2 3 4 5 6 7 8, and then in the other way we can write it like this is 60, this is 59, this is 58, this is 57, 56, 55, and 54. I hope you understand. So yeah, now they looks like that. They looks like this. Is it fine? Now it shows that you need 60 cycles, 60 samples to represent 31 cycles, which actually give you the period. Before or after that you are not getting, so before that you are not getting your same phase back, so you have the same phase after 60 samples. So that's why you need minimum 60 samples to complete these cycles. Okay, on the other hand, what happens if I change the frequency a little bit? Frequency means this analog frequency. This analog frequency, if we change the frequency a little bit, then it might happen that, okay, let me choose another color. It might happen that this is the first point, the second point moves to this. Okay, so two samples. Okay. Okay, let me choose this one. It will helpful for us. Let me, this one and this one and this one, you are changing the frequency a little bit and makes the signal very similar to that one. So let me draw this. Okay, so what happens, previously the signal looks like this. They are not in the same phase, so okay, bit earlier. Okay, what does it mean by this? This point, you are searching for the same phase again, but unfortunately, where is the same phase? This could be the point for the same phase, but you are not finding that. So that's why you need to continue and you are searching for that one. And just believe that, okay, you need 31 sample and 31 cycle and 60 samples to complete the whole cycle or finding the same phase back, and this is your F1. Now, if you change your frequency a little bit, then it might happen that you are changing your frequency a little bit. you are decreasing. Let's say you are decreasing your frequency, and fortunately, what you got, you have this point 1 and 2. After that, you are getting the same phase back. So how many samples you need to fulfill the period? You need basically 2 samples for a single period. So you can say that, okay, my F2 is equals to 1 divided by 2. Basically what happens, you can also write it like this: F2 is equals to 30 over 60. Those are the same. What you have done? You have done nothing. You haven't changed the sampling frequency. You make the sampling frequency fixed. What you have done, you have just changed the analog frequency a very small amount, comparing it to the previous one, and that will show that your discrete signal period, the discrete signal period is actually changed a lot. Previously it was 60, now it is only 2. This 2 means 30 by 60. It can be like any value, let's say 60 by 120, no problem, or 120 divided by 240, any value, because it is a periodic one. So after 2 samples, each 2 samples, you got the period. So have you understood the fact? What does it mean by F1 is equals to 31 by 60, or F2 is equals to 30 divided by 60? This 30 divided by 60 is nothing but 1 divided by 2. What does it mean by 1 divided by 2? You need 2 samples, just 2 samples to fulfill the cycle. And here this 2 is the fundamental period of the cycle of that discrete signal. Okay, so if this sort of question arises or been asked during the exam, justify. You need to justify this statement. Okay, so you need to justify. Okay, sorry, the lower part we have. Yeah, if I have given this statement, a small change in frequency can result in a large change in the period of a discrete time signal, then how could you justify this? With definitely graphical representation, you need to justify this fact. Okay. Okay, if you have any question, just don't hesitate to raise the hand and ask me the question. So this is number 1 characteristics we have gone through. The second one is discrete time sinusoids whose frequencies are separated by an integer multiply of twice pi are identical. So if you have a signal frequency, let's say omega 0, in which domain? Could you please answer? This frequency at which domain? Analog domain or the discrete domain? Sorry, time domain or in the discrete domain? This omega 0. This omega 0 in the time domain.
So discrete domain.
Yeah, you should raise the hand. Okay, yeah, thank you for your response. This is in the discrete domain. So we are talking about the characteristics in the discrete domain. That's why omega 0 is also discrete. So if we have omega 0 and another frequency like omega 1, which is equals to omega 0 plus twice pi, then these two frequencies like omega 1 and omega 0 looks identical. What does it mean by identical? Okay, let's give you an example. Let's say I have a system. System means that could be a filter. Okay, let's say this is a low pass filter. Low pass filter. For example, it can be any system. I have given the input as omega 1 and the output, after having this low pass frequency, I have found that this is omega 0. Practically, okay, so it can be written as, okay, so let me give this example in other way. Let's say we have omega 1 plus noise, and in the output, what we want to do, we want to cancel the noise only. So in the output, it should be like omega 1 only, but unfortunately, it looks like omega 0. That means you have enter omega 1, you are expecting omega 1 at the output, but unfortunately, it looks like omega 0, and that is called the identical of the signal. So to be more specific, what does it mean? Let's say you have an analog signal. You have an analog signal, and you sample that. So you have sampled it with specific sampling frequency. Okay, whatever the sampling frequency you have chosen, you have sampled that. Okay. Whenever you have sampled it, what would be the sampling frequency? Let's say the sampling frequency, sorry, the discrete domain frequency or relative frequency is omega 1. Now you have given this to a low pass system, low pass filter, and after that you want to get back your original signal. As you know that from the analog to the digital. So what is analog to digital converter? How does it do? It actually have a chopper circuit. So you are putting on and off, on and off. By on and off activities, you are getting those samples. So I believe you understand those facts. What about the digital to analog converter? This is nothing but a low pass filter. You can have a low pass filter. That means you can put a capacitor across the output. So this is your output and this is your input. If you are putting your digital input there or discrete input there, in the output you will get the analog output. So analog means what? You have the digital output, digital input like this, those dots. If I can make the point more clear, you have only those stems. You have only those stems. You don't have the red line. Okay, so you can just only putting those stems as an input to the low pass filter. Now, how does it looks like the output? The output looks like this. Output looks like this. So the green one is the output of the low pass filter. So it is omega 0. So you have given omega 1. You have given omega 1 a discrete signal, but you have got the output as omega 0, and they are called the identical signal. You don't expect that, but there are some bad things, bad portion, there are some good portion as well. So this is known as the identical. So I'll give more example, practical example as well. So for now on, what you can understand from the analog domain, you are giving a 10 kilohertz signal to a filter, and in the output, if you got 1 kilohertz signal, then this 10 kilohertz and 1 kilohertz works like an identical signal. That is called the identical, or you can say these are the alias signal to each other. These are the alias signal to each other. Okay, so this is the mathematical representation. So these are the mathematical representation. After that, we'll also talk about the graphical representation as well. Okay, so first the mathematical representation. So let me recite the statement again. Discrete time sinusoids whose frequencies are separated by an integer multiply of twice pi are identical. That means if you have some frequency omega k where twice pi omega 0 is the fundamental plus twice pi k, where k is the value like k is equals to 1, 2, 3. So they are identical. So all the values are identical like that. Okay. So it has been discussed in the subsequent sections. So let me go one by one. So I believe that you understand this expression. That means what we have done, we are increasing the frequency, discrete frequency by twice pi. And then we elaborate those things with the same logic. Since this is twice pi n, which is a multiplied of twice pi, where small n is an integer. Small n is always integer. It can be 0, 1, 2, 3, 4, any value. So it will not make any impact to the cos format. So you will have the same thing across the cos function. So that's why we can write that cos omega 0 n plus theta. So that means it is very important to understand that what we can write, the cos omega 0 n plus twice pi n plus theta is equals to this one. So that means they are identical. This one is omega, let's say omega 1, and this one is omega 0. So omega 0 and omega 1 is identical. Similarly, we can write that, let's say cos omega 0 n plus twice pi into twice n. That means 4 pi. If we write like 4 pi n plus theta, it is also identical to cos omega 0 n plus theta. Okay, they are identical. So from the mathematical point of view, we can prove it very, very easily by these two lines only. Then there are some description how we can represent those things. Okay, what are the frequencies? They are identical. We can represent like this. Just gone through this. There is nothing to describe at this point. In practice, how do we represent the things? I have given one example here. Let's say omega 0 is equals to pi by 6. I believe that you know what does it mean by pi by 6, by the value f is equals to 1 by 12. What is that? You need 12 samples to represent a full cycle. So that is your f. Now, if I have another signal, another frequency omega 1, which is separated by twice pi, then we can write omega 0 plus twice pi, which is equals to pi by 6 plus twice pi. We can write it 13 pi by 6. So what is the value of f1? F1 is equals to 13 divided by 12. 13 divided by 12. What does it mean by 13 divided by 12? Any of you? 13 divided by 12. Yes, 180.
It means that we need 12 samples to represent 13 cycles.
Exactly. So you need, and after that, you need to also finish like this. You need 12 samples to represent 13 cycles, full 13 cycles, which makes a period, Okay, 13
Okay,
cycles,
okay,
yeah, that actually makes a period. So this is your fundamental period. Okay. Okay, no problem. Thank you for your response. Yes, 58. I believe that you also give the same response.
Yes.
Okay, so we have F1. Now, according to the statement, this F, let's say F0 and F1, they are identical. They are identical. What does it mean? They looks the same. They looks the same. In which domain? In the analog domain. In the discrete domain, definitely they are different, because f0 is equals to 1 by 12 and f1 is equals to 13 by 12. Definitely you can understand that they are they have the difference. But what about the represent in the analog domain, how they looks like? How they looks like? They looks like the same. So I'd like to request you to draw this and then add all the stem, and then you can find that this analog signal is exactly looks like that analog signal as well, and they are identical. Okay, they are identical. Let me give you one example, starting with the very beginning. Let's take a very simple example. Cycle 1, cycle 2. Yes, 132.
Sir, isn't F0 and F1 the frequencies of the discrete signals that we made?
Yeah, of course. They are the
So-
discrete frequency.
Sir, so by analog domain, did you mean time domain?
Yeah, analog domain means the time domain.
Okay, sir. Thank
Yeah.
you, sir.
So try to draw this 1 divided by 12. 1 divided by 12 and 13 divided by 12. Definitely it's difficult to draw this 13 divided by 12, but at least you can have the idea. Okay, let me give another simple example by which we can understand this fact. Okay, how they looks like, or they are alike of the fact. So for a single cycle, okay, if we have 1 divided by 2, let's say we have f1 is equals to 1 by 2. First of all, step number one, we have taken a 1 hertz signal. Very simple, 1 hertz signal. 1 hertz means you need to represent this. What is the time? This is 1 second. So 1 second. So that is the definition of 1 hertz. So this is our analog signal. And now we have sampled it and we got the discrete signal, and the discrete signal frequency, we got the relative frequency is equals to 1 by 2. What does it mean by that? Okay, it will be better to take the line over this. Okay. The cause part will give us some kind of advantage for the sampling, okay, to understand the point more clearly. Okay, so let me choose it. Okay, then where is the t? Okay, so this is the whole cycle. This is t is equals to, not t, this is 1 second, the period. So this is tp. And now we have sampled it and we have found that, okay, f1 is equals to 1 by 2. So if that is 1 by 2, then where are the samples? The sample is 1, 2, and then this. Okay, and of course it will continue. So I have maintained first cycle, and let's say continue the second cycle as well. Second cycle, continue up to second cycle. Be very careful what I am explaining here. Though this is a very simple example, sometimes it will help you to understand the other fact as well. Okay, now if we have another signal, let's say f2 is equals to 3 by 2. 3 by 2. What does it mean? 3 by 2. 1, 2. Three by 2. Means you need 3 cycles, you need 2 samples in 3 cycles to complete the period. You need 3 samples. Sorry, yeah, you need 2 samples. And how many cycles? 3 cycles. So where is the 3 cycles? So this is cycle number 1, this is cycle number 2, and this is cycle number 3. So if it starts with this, okay, so the green dots, now I'm putting the green dots. Of course, after 3 samples, 3 cycles, you will have that dot over there, okay? So that is the definition of period. Now in between, how many samples you have? You have another samples, because the total sample number is 2. So this is number 1, there would be another samples, there would be another sample, and then you have the other sample. Can you follow me?
Yes, sir.
Okay. So where would be the other sample? Definitely in between. So the 50% of that. So where would be that point? Maybe at this point. Isn't it? Are you with me?
Yes, sir.
Okay, we are dividing the whole spectrum in 2 parts. So this is 1 point, this is another point, and after that we have that point. And it shows that this is F2, that means 3 by 2. It is 3 by 2. Now, the fact is, if you have F2, what was the analog frequency? What was the input analog frequency? It was like this, 1 hertz. And then you sampled it, and you have the discrete frequency like F1 is equals to 1 by 2. Okay, fine. Now, what you have done, you have changed the sampling frequency, and you may find another discrete frequency like F2 is equals to 3 by 2. 3 by 2, and I have already drawn this. Now, if you put those dots, this is dot number 1, sample number 1, sample number 2, and sample number 3, and more and more to the low pass filter, then how the signal output looks like? The signal looks like this. The green should be taken as green. Something like that. And it will continue. Definitely it will goes down and up. So this is a full cycle or a half cycle? It's a full cycle or half cycle, what I have drawn. Full cycle or half cycle? I'm waiting for the response. Yes, 90?
Sir, it looks like half cycle, but should be a full cycle.
And this is half cycle, of course, because this is a higher value, then lower value, then higher value, and then after that you have the lower value. So where is the is a full cycle? How could we maintain that this is a full cycle? Because we have the higher value, then goes to the lower value, then goes to the higher value. They have the same phase, so that this is a full cycle. This is not the half cycle, isn't it?
Yes, sir.
This is a full cycle, like this. Like cos wave, you have higher value, lower value, and higher value. This is a full cycle. Because you have the same phase, that's why this is a full cycle by the definition of analog signal. So this is a full cycle. Can you find out what is the frequency of this green line? What is the frequency? Frequency means whenever I am talking about frequency, that is always analog frequency. When I have talked about a relative frequency, then that is the discrete frequency. What is the frequency?
Sir, 1 by 3 hertz.
1 by 3 hertz. So we start with 1 hertz, and now we come up with the value that the frequency is 1 by 3 hertz. So this 1 by 3 hertz is actually called the alias signal. This is the alias signal of the 1 hertz signal. So you start with 1 hertz, but you come up with the frequency that 1/3 hertz. It looks like 1/3 hertz. So if I can make the story clear to you, that you are having the signal 1 hertz at the input, you are choosing a sampling frequency fs, for which you have generated f2 is equals to 3/2. What would be the output frequency? What would be the output frequency? You have found that the output frequency 1/3 hertz. Normally, you need to choose your sampling frequency in such that you have put in 1 hertz signal, the output should also be 1 hertz signal, because this is a digital domain. There you need some processing. After the processing, you should come back to your original signal. For that, what you need at least, how many samples you need to retrieve your original signal back? This is very important. How many samples you need at least to retrieve your original signal back? You'll find that at least there. So you need what? You need at least 2 samples to get back your original signal. Otherwise, you'll find that your original signal will not be discovered anymore. Then you start with a frequency, let's say 1 kilohertz. If there is a 10 kilohertz, the output is like 1 divided by some, let's say 3.33 kilohertz, 1/3 of that. So you start with 10 kilohertz, but output looks like 3.3 kilohertz. You don't have any capability to go back to your original signal. And here, this 10 kilohertz and 1.33 kilohertz, they are looks like the same, and they are the alias of that one, and they are identical. They are identical signal in the analog domain. What about the what about the discrete domain? In the discrete domain, they have mentioned in this way: if they are separated by twice pi, we have already proven that if they are separated by twice pi. Now comes to the omega. In the omega platform, if this is 0, if this is pi and this is twice pi, if this is minus pi, and let's say we have minus twice pi as well, then whatever you have found there, whatever you have found in between this in the frequency domain, or from 0 to twice pi, so the 0th frequency will be identical after twice pi. The pi will be identical after twice pi, that means at the location of the thrice pi, and similarly. So that is why people are writing like this, okay? If this is a minus pi to plus pi, you have everything like this. It will be identical with respect to twice pi, will be like this. It is in which domain? This is in discrete domain. They are in the discrete domain. They are identical. They are identical in the discrete domain. If you come back to the analog domain, you will find that the frequency will changes. Frequency will changes. How the frequency will changes? Let me discuss it here. Like, for example, you had a discrete frequency at this location, any location. It will be identical where? Before twice pi. Where is that? Let's say this, before twice pi. So this is the distance before twice pi. So this frequency is identical to this frequency according to our definition. We have already shown this definition to us, to you, okay? According to this, And now it's very interesting that this one is also identical to that one because it is a negative frequency. Let's say negative omega 0 is equals to the positive omega 0. Now we can say that similarly, this frequency is identical to this frequency. That is how we can find the identical frequency. So let me describe the things again. It's very important in the frequency domain. So this is from minus pi to plus pi. This is twice pi. This is thrice pi. So any value at this point is equivalent to the point before twice pi or after twice pi, any of those. And this one is definitely identical to the positive because this negative frequency is only for the mathematical purpose. There is no physical instant of the negative frequency. So then we can mention that this frequency is of course identical to that frequency. So you can start with this. You can start with this, but you are actually end up with this frequency. You can start with this number 1 and you will end up with this number 2. This is in the discrete frequency. If it is represented as F1 and this represent as F2, then F1 and F2 are identical. F1 is higher or F2 is higher? Just quick response. F1 is higher or F2 is higher? Which one is higher? F1 or F2? Yeah, 90?
Sir, what do you mean by higher?
Higher frequency, higher value. F1 is higher value or F2 is higher value?
According to sample number, F2 is higher value. According to phase, they are same.
Of course, F1 is higher.
F1 is higher.
Yeah, of course, F1 is higher. You know that I'm representing this point as F1. F1 is higher than F2 in the discrete domain. Whenever we are talking about they are identical in the analog domain, not in the discrete domain. I have already mentioned that. Let's say I have mentioned F1 is equals to 1 by 12 and F2 is equals to 13 by 12. Are they identical? No, they are different. But in the analog domain, they looks identical. So that means you start with a higher frequency. So F1 is a higher value. You start with a higher frequency. It means that the analog frequency is also higher. The analog frequency is also higher. Okay. But you come up with a discrete frequency lower value. That means that the analog frequency also lower. So that means you come up with a lower frequency. You start with a higher frequency, but you come up, you have the lower frequency at the output. In the next class, I will discuss the same issue with some example. What is the condition? What is the condition so that you don't have the aliasing? You know about the Nyquist theorem. We'll give some example of the Nyquist theorem by which we can understand the fact, inshallah. Okay. Okay, thank you very much for your participation. And now I am stopping the recording. Thank you.